Hello fellows. The most amazing thing about our universe is, perhaps, its size. How unimaginably big this universe is. But, perhaps, this is the most disappointing aspect as well. Think about it, if today we use our powerful telescopes to find another planet like Earth in a galaxy, which is suitable for humans to live on, it will take centuries for us to reach it. In fact, for all individuals leaving this galaxy is impossible. Now everyone knows that the Earth is in the Milky Way galaxy. And the closest galaxy to the Milky Way is Andromeda Galaxy. Approximately 2.5 million light years away from the Earth. So if we use a spacecraft to reach there with the usual speed of 28,000 kilometers per hour, it will take 94.5 billion years to reach it. Not only that, if we can somehow make the technology travel at the speed of light, it will still take 2.5 million years to reach there. This is truly disappointing. What is the point of finding all these planets when we will never be able to travel there? But if there were a shortcut to travel outside the galaxy, a shortcut through which we can travel across million light years in a few months, then these things become interesting. These shortcuts, my friends, are wormholes. The 2014 film, Interstellar, my one of favorite film, in this movie, it is shown that when Cooper and his team leave Earth in search of other habitable planets, in search of other planets like Earth, they travel to another galaxy. From their galaxy to another galaxy, they travel through a wormhole in a matter of minutes. This is the scene in the film when Cooper's team passes through the wormhole. According to the film, this wormhole was discovered near the orbit of Saturn by NASA. It is mentioned in the film many times because it plays an important role in the plot. But the most interesting thing is that this concept of wormholes is not science fiction. In fact, it is based on real science. What are wormholes? And how can we use them? Before understanding all this, we have to come back to Einstein's theory of relativity. When Albert Einstein wrote his theory of relativity, he wrote it in a set of equations. The set of equations is called Einstein's field equations. It was first revealed publicly on 25th of November 1915. When Einstein submitted his paper to the Prussian Academy of Science in Berlin, Germany. In total, these field equations are made up of 10 different equations. 10 nonlinear partial equations. But in short, they can be represented by only one equation. And that equation looks something like this. Don't worry, we won't go into the mathematical details in this video, because this one equation has a lot of complexity. If you expand this one equation, you can see these steps. Even if you love math, you will get dizzy after seeing this. Broadly speaking, these equations tell us how matter and energy influence the curvature of space-time. Albert Einstein said that to visualize this, we need to imagine a big mesh. When you place objects on this mesh, it bends down due to the weight. The space-time mesh also bends in the same way, it curves with the weight of big planets and stars. The more the gravitational force of a planetary object, the more the space-time mesh will curve around them. Now the interesting thing is that Albert Einstein himself was not able to solve his field equations completely. He had just found an approximate solution to his equation in a specific case. The first person who solved these field equations was Carl Schwarzschild in the year 1916. He calculated exactly how much the curve of spacetime bends and to what degree and how in case of a single ball of mass. It was the solution by Carl Schwarzschild which helped scientists understand the concept of singularity. What would happen if this mass becomes infinitely dense? The curvature of spacetime would wrap around it so tightly that this region would pinch off from the rest of the universe. With this, the scientists were able to theoretically prove the concepts of black holes. This was proven about 100 years ago. Actually, decades later, for the first time in 2019, scientists were able to take a photo of a black hole. This picture was further sharpened by AI artificial intelligence, on which I have already made video about that. You can see that in cards of this video. So basically, what I want to say is that one of the solutions to these field equations was black holes. Theoretically, we already knew about the existence of black holes about 100 years before they were discovered. And the thing is, friends, that another solution to these field equations is wormholes. You might be thinking, how can we solve one equation and get two solutions? Well, I would say that you should remember studying quadratic equations in school. This simple equation also has two solutions. X equals -7 and x equals 6, both are correct. So, if you say Einstein's field equations, they are much more complicated. Actually, there can be numerous solutions to these. Wormhole is one such solution. And its scientific name of the wormhole solution is the Einstein-Rosen bridge. This name is derived from Albert Einstein and his assistant Nathan Rosen, who worked together and came up with this solution in 1935. So it is very easy to understand wormholes. It is basically a shortcut which connects 2 points of space-time. First, I will explain things in 2 dimensions so that it is easy for you to understand. Look at this paper. This paper has 2 points A and B. If you want to go from point A to point B using the short route, which route can it be? The straight line that connects A and B. Yes, displacement. There can be no shorter route in 2 dimensions except the straight line connecting both points. But if this 2-dimensional mesh is bent into 3 dimensions, you will see new paths emerge. If I make a path here between these two, then literally, a shortcut has been found to go from A to B. Which is much, much shorter as compared to that displacement. Wormholes are also doing the same thing. In our 3-dimensional world, we think that the shortest way to go from Milky Way galaxy to Andromeda galaxy is 2.5 million light-years long. But if our 3-dimensional space is curved or bent into the 4th dimension, then it is possible that we can find a shorter, better shortcut. Now, it is very difficult for us to imagine the 4th dimension because we all live in 3 dimensions. But to some extent, you can understand it better if you compare 2 dimensions and 3 dimensions. In 1957, scientist John Wheeler published a paper on Einstein's Rosen bridges. He compared it with a similar analogy. He gave an example of an apple and an insect is eating that apple, a worm. It reaches from one side of the apple to the other while eating it or traveling through the middle. Instead, on the surface of the apple, like our aeroplanes travel around the surface of the Earth's circumference. By doing this, the worm will travel a shorter distance. In a way, it has taken a shortcut in space-time. And this term was named by Wheeler as a wormhole. And this is where the word wormhole originated. When you search the word wormhole on the internet, you get to many such diagrams. Basically, the same thing you see with the paper. Here it is, imagine that we have a space-time mesh, on which there is an object with an extremely strong gravitational force. So strong that the curvature of space-time has bent so much that it has pierced through the other side. The space-time mesh has folded on itself. And this wormhole has become a shortcut to travel from one galaxy to another. But in all these visualizations, the problem is with the dimensions. We try to represent a wormhole in 2 dimensions. But as I said, wormhole works in 3D and 4D. So in reality, if a wormhole exists, it will look like a spherical ball. Here, it is important to mention that the concept of wormholes for now, as of 2023, is just a theoretical concept. It has been theoretically derived as a solution to Einstein's field equations. In movies, scientists have tried to visualize it. Many theories have been formed about it, but practically no one has seen a wormhole yet. Scientists don't know whether wormholes really exist or not. But if wormholes exist, they will work as a time machine too. Just imagine that you will be able to travel millions of light years in a few minutes. This means that you can reach there even before light. If the light didn't reach there, then basically you have jumped from one place in time to another. Now it's a different thing that what if wormholes do exist, can humans even travel through them or not? Many practical problems arise here. If wormholes are to be considered real, the first question is, how will the opening of the wormhole be formed? We need extremely heavy gravitational force here. Where can we find this gravitational force? Right from a black hole. Einstein and his assistant Rosen theorized that only black holes can have such a gravitational force. That they can open up these tunnels of wormholes. Everything is attracted to black holes. Everything will be attracted to it and will flow through this wormhole through this tunnel. But the next question is, what will be on the other side of this tunnel? If there is a black hole on the other side, then there will be no way to get out of this tunnel. You will be trapped inside this tunnel. Basically, in that case, this wormhole will not be a tunnel to go from one place to another, but rather it will be a trap. There should be something on the other side which is the opposite of a black hole in every sense. Something which is as powerful as black holes but works in the exact opposite way. Something that instead of attracting things towards itself, send things away from itself. So that an exit point can be created. And here, enters in our story, the white holes. Once again, white hole is a concept that has been proved theoretically by Einstein's field equations. Apart from black holes and wormholes, white holes are another solution to these field equations. What are these white holes? Let's understand it in next video and other ways to reach other galaxies.